Hello everyone, my name is Haikang and I'm from Fudan University. Today my topic is Edge Computing System based on smart methods for sleep posture recognition in IoMT. In the field of healthcare, sleep posture has been proven to be a crucial index for sleeping posture monitoring. Wrong sleep postures may increase the burden of muscles and lead to breathing disorders like sleeping pain, affect the blood circulation. Therefore, a sleeping posture recognition system that enables long-time sleep posture monitoring and can be integrated into IoMT systems is needed. Recently, quantities of methods have been proposed to recognize sleep posture. These methods can be classified into three categories. The first is to use video cameras to monitor sleep postures, but this method is susceptible to batteries and light, and may also produce privacy leaks. The second is to use a variety of wearable sensors to monitor sleep posture. However, with the attached sensors, natural sleep may be disrupted. The third is based on the pressure sensing smart method to achieve safe, convenient, and comfortable sleep posture recognition, which can be applied in hospital or home scenarios. However, all of the methods mentioned above are unable to deploy in embedded systems for edge computing due to the complex algorithms, and therefore cannot be integrated directly into IoMT as an edge device. The edge system is shown in this figure. When a person lies on the mat, the force sensing mat acquires the voltage in different areas, and then the voltage goes through the signal control and acquisition circuit into the embedded system. Finally, the embedded system is used to convert the voltage signal into pressure distribution map and implement the sleep posture classification. The electrodes and the pins of the mat, the force sensing resistors, and the depth acquisition circuit and the embedded system are shown in these figures. To implement edge computing, the STM32 system, a cost-effective embedded system, is used as a computing platform. This system is based on STM32 F746ZGTX microcontroller with 216 MHz clock speed, 1 MB of flash memory, and 314 KB of RAM. It provides serial ports, GPIO, and ADC. Compared to expensive servers, it costs only $5 and can be used as an edge device in IoMT. Meanwhile, it also can run edge algorithms due to its high mean frequency and sufficient memory. The pressure distribution when one hand is pressed on the mat is shown in Figure 2. Due to the high sensitivity of the mat, the position of the palm and the fingers can be detected. To implement real-time edge computing in IoMT. A lightweight algorithm for sleep posture classification that can be deployed in an embedded system needs to be designed. In this section, an AgNet-based sleeping posture classification algorithm is proposed as shown in this figure. It consists of four steps: pre-processing, AgNet pre-training, model quantization, and model deployment. The sleep postures are classified into four categories: supine, prone, right, and left. to eliminate the internal noise, high-frequency noise, and redundant information due to the softness or thickness of the pressure sensors embedded in the mat. Threshold filtering, Gaussian filtering, and adjacent affected noise removal are used in pre-processing. Convolutional neural networks (CNN) is a feed-forward neural network, and it has a good effect on image recognition. However, the increase in classification capability comes with other drawbacks. The size and the computational complex of the model become high and beyond the capabilities of the IoMT system. In this paper, edge computing contains one SE block, 5 bottleneck blocks based on MobileNet v2, and one dense layer as shown in this figure. The description of each layer of the network is shown in Table 1. C denotes the number of the output channels, S denotes the thread, and T denotes expansion factor. The SE model adaptively assigns the weights of different future channels by calculating the interdependency between channels. MobileNet v2 was proposed by Google in 2018, which is based on the dipwise separable convolutions and inverted residual structure called bottleneck block. In this paper, post-training integral quantization is proposed for model compression after the AgNet has been trained. Post-training integral quantization is to convert 32-bit floating point numbers, such as weights and activation outputs, to the nearest 8-bit fixed point numbers for the already trained float model. The operation can be described by this phenomenon. To evaluate the feasibility of the system for sleep posture recognition, short-term and overnight experiments were conducted as shown in this figure. 16 subjects were included in the short-term experiments and 5 subjects were included in the overnight experiments. The mat was placed between the subject's neck and hips and was parallel to the subjects. There were a total of 1,059 samples for the short-term experiment and a total of 20,121 samples for the overnight experiments. We performed the AgNet on the short-term and overnight database respectively. The overnight database is used as a test set to judge the effectiveness of the proposed algorithm, while the short-term database is used as training set and validation set. Table 2 shows the accuracy of the AgNet model and other models for sleep posture classification. Compared to other models, the AgNet proposed in this paper significantly reduced the size and computational complex of the model while achieving competitive accuracy. Due to the preprocessing operation, we have simplified the pressure distribution images and removed redundant information, thus achieving high accuracy with the AgNet. Meanwhile, by applying the SE models to the input of the network, attention is added to the input channels. Thus, the network pays more attention to the channels that are more sensitive to the posture classification task, while improves the efficiency of the model. Table 3 shows the comparison of the AgNet before and after quantization. Yes, the table 3 shows the comparison of the age rate before and after quantization. It can be seen that the size of the model is reduced by 16% after quantization, but the accuracy rate only decreased by 0.64%. This proves that the quantization can be indeed significantly reduce the model size and the computational complex while ensuring classification accuracy. After the model is quantized, we deploy the agent in STM32 to evaluate the performance. Also, we deploy the unquantized agent in STM32. Table 4 shows the performance and the memory usage of the two models in STM32. Since the weights and activation values are quantized from 32 bits to 8 bits, the memory usage, the computational complex are reduced. Although the MACCs of the two models are similar, the CPU clock cycles required to execute a single operation are much different. Therefore, the inference time of quantized model is only the 13.7% of that of the unquantized model. Together with the data acquisition and the preprocessing algorithm, the quantized model performs a complete sleep posture acquisition and classification algorithm in less than 16.5 milliseconds. This proves that the system proposed can be used as an edge device to achieve long-term sleep posture monitoring in IoMT. In this paper, for offering an edge computing system for sleep posture recognition in IoMT, a smart-made system based on EdgeNet is proposed. The algorithm framework consists of preprocessing, EdgeNet pre-training, model quantization, and model deployment. Experimental results show that the accuracy of the short-term experiment is up to 92.1%, and the accuracy of the overnight is up to 75.43% before quantization. After quantization, the accuracy of the overnight is up to 74.79%, and the runtime of the complete algorithm is about 65 microseconds in the STM32 system, while shows that its ability to provide sleep posture recognition in IoMT. Compared to other methods, our system has the advantage of the low cost, low latency, low power consumption, high reliability, and no privacy concerns. In the future, the MET system can still be enhanced by integrating embedded network training algorithm and Bayesian detection. That's all. Thank you.